plus I, all divided by, you know, minus 2 times the square root of 9I, I think. Because when I put that in here, I just get minus 2 of those, which I could, you know, rewrite this if I want. I sort of want to. That's 1 plus 81 minus I divided by 2 times the square root of 9I, but that was, I'm going to put in what the square root of 9I is now, which is 3 e to the pi I over 4. You know, and anyway, so like, I don't want to continue down this path, but it's fairly clear how to put it into Cartesian form at this point, right? If you wanted to. But I mean, I could stop. I could content myself with, okay, there's A, right? And how do you calculate B? Well, you do the same thing, right? But instead of putting the limit going to minus the square root of 9I, you go to plus the square root of 9I. So if you remember Calc 2, the way we did this was just to multiply both sides by the denominator, right? And that way it's still legitimate. This is just like another notation for that idea, guys, you know? So minus 2z, or the 2z minus 81 plus I is A times what? Well, A times z minus the square root of 9I plus B times z plus the square root of 9I, right? So if you just look at that equation comes from taking the limit. So essentially this stems from like multiplying r mn of z by the denominator. Okay. Yep. Yeah.
So can we still match coefficients? That's still
yeah. I mean, that's essentially what this is saying. He has a nice overarching like technique in here. There's an example in the book which makes better contact with the more subtle thing, which you haven't seen yet. Let's see here. So it's a lot to write out, but I guess I should. So like this theorem 2. Actually, I'm not sure how much more we're going to get out of it with me writing more in this section, because what's left to write is a lot to write. But let me take my medicine. Here we go. All right, so theorem 2. Theorem 2 on page 105. It gives the sort of general partial fractions decomposition for a rational function, a proper rational function. All right, so start over here. R, M, N, Z. And so what you got is A0 plus A1Z plus plus AM, M as in mommy, Z to the power M, divided by B sub n, where that's non-zero, times z minus, let us say, zeta 1 to the power d1, z minus zeta 2 to the power d2. You guys, I can pick a different letter. Let me pick a different letter. I'm going to lose all you guys because I'm using the wrong letter. Let's go with alpha. Alpha 1. Alpha 2. There we go. Everybody can write alpha. Dot, 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 z minus alpha sub r to the dr power. All right. Then this can be written as the following. You can write it as a sub 0 upper 1 parentheses z minus alpha 1 to the d1 power plus a parentheses upper 1 sub 1 z minus alpha 1 to the d1 minus 1 power plus dot, 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 dot. Eventually you get to the a upper 1 to the d 1 minus 1 in his indexing, z minus alpha 1, just like that. Then comes the next one, plus a sub 0 upper 2, z minus alpha 2 to the d2 power, plus dot, 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 dot. Eventually you get to a upper 2 to the d2 minus 1 divided by z minus alpha 2. And this goes on. All right. Eventually you get to a sub 0 upper, how many do we have? R of them, r, divided by z minus alpha r to the dr power, plus dot, 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 plus a upper r to the d sub r minus 1 z minus alpha r. And that is the partial fractions decomposition. And it's unique up to reordering. All right. The book doesn't say it's unique, but it is up to reordering. And so let me give you some more terminology here. Basically, what's on the first line. So this is terminology we'll come back to much later in the course, but I think since we got this on the board, let's talk about it. So this is the piece, the part of RMN which is singular. At z equals to alpha 1. All right, just this piece. And if that's the partial fractions decomposition of the rational function, we say z equals to alpha 1 is a pole of order d1. Okay, and like exactly the same comment applies to alpha 2. That's a pole of order d2, all the way on out to this one, out to alpha r, which is a pole of order dr. What's cool is the book actually gives you a formula for like calculating the jth one, all right? And so I'm just going to let you guys investigate that in the homework. Basically, it's just a technique. And here's how, if you want to get the jth in parentheses lower sub s, what you do is you take the limit as z goes to, in our notation, alpha sub j. All right. And check this out, 1 over s factorial, the s derivative with respect to z. And what you got to do is you got to multiply z minus alpha sub j to the power dj r m n z. And that right there will pick off the coefficients in the partial fractions decomposition. Again, this presumes that this is a proper rational function. Okay? And that means that m is strictly less than n. And n, by the way, here is equal to d1 plus d2 plus dr, to be clear. It's the sum of the orders of the poles. I don't know if you guys remember or not, but finding the partial fractions decomposition in Calc 2, it is trickier when the root is repeated, right? When the roots are distinct, essentially the algebra I just went through in example 2 works out. But if the roots are not distinct, if they're repeated, it was a bit touchy, the method to get the coefficients. And this gives you a stone cold formula to calculate the coefficients, all right? And the reason that this is the formula is actually somewhat apparent if you just think through what happens when you take this expression, right, and you multiply it by z minus alpha sub j to the dj power, what happens? So if you we can think about, for the sake of this discussion, let's think j equals to 1, okay? If we can understand j equals to 1, we should be able to do more arbitrary j. So think j equal to 1. What would happen then? When you multiply this, right, by z minus alpha to the d1 power, this term right here becomes just this term just becomes a sub naught 1, right? And this one, you get the 1, 1, and you get z minus alpha to the first power here. All the way on out to here, you get z minus alpha 1 to the d1 minus 1 power. Right? If you think about multiplying by this factor. So if you don't even differentiate, right, if you just take the limit as z goes to alpha 1, what happens is everything else here goes to 0 because you've just multiplied everything else here by this z minus alpha 1 to the d1 power, which goes to 0. And none of these other things diverge at any of those points because we're assuming that the roots to the polynomial, to the denominator, the alpha 1 through alpha r are distinct. So this stuff all goes to 0. And everything else goes to 0 because you've got a non-trivial power of z minus alpha 1 to a power here and all the way out to here. The only thing that remains is this. And that's why the formula works for s equal to 0. When you take s equal to 1, you're taking this expression and you're differentiating it. So when you differentiate that, it gets rid of this piece. And all of this stuff is still just limiting to 0 because it's, again, multiplied by this, which when you differentiate one time, it still gives you something that differentiates to 0, assuming that d sub j is larger than or equal to 1. If d sub j is equal to 1, then I don't believe you different. I mean, well, anyway, we have to think through the combinatorics I'm talking about just now. But anyway, when you differentiate that, this piece goes, and then you just have this piece. And when you take the limit, you just pick up that. But as you differentiate more than one time, you start picking up the numbers. Like the second power, you get a 2 times a 1. And the third power, on the third derivative, you get a 3 times a 2 times a 1, which is why you have to divide by this to compensate for the, the combinatorial factor of s factorial you're picking up from the s-fold differentiation there. So yeah, I was going to work through, my plan for today was to work through this example in the book, example 5, but you guys had another example for me to work at start of class, which was easier, so thank you. Anyway, I will push your homework back to Tuesday, but it's not for your best because that quiz is still due Thursday. So, next week is going to be very crammed unless you get most of the homework, which was originally due Thursday, done this week. But, yeah, okay.
And are we going to do inverse functions?
Yeah, well, Thursday. We started to do that already. Like I talked about the derivative of log, and but yeah, well, that's the, yeah.